So probably we should start. So welcome to our online Zoom colloquium. Before we start the colloquium, let me briefly introduce our speaker, Naomi Ginsberg. Probably many of you know that she is a faculty member of the physics department as well as the chemistry department. Naomi came to Berkeley as a Seaberg Fellow in 2010. And then she joined our faculty in 2011. Besides, being a faculty member on campus, actually, she also affiliated with LBL, in the material science division. And she is also a member of the Catholic Energy Nanoscience, the Institute. Naomi, has received many awards. So let me just tell you a few that I am aware of. She was a Parker Fellow in 2011 and a Sloan Fellow in 2015. And this year, she received the earlier career award in experimental physical chemistry from the American Chemistry Society. So besides her outstanding achievements in research, actually, she also received many recognitions in her teaching. Certainly on campus, she received the teaching award in the chemistry department. And more significantly, actually, she awarded the Drivers Teaching Scholar Award in 2016. Now she has certainly very broad interest overlapping physics and chemistry. And right now, research is focusing in ultra fast energy flow in natural and also artificial light harvesting system. And she is also studying living things and molecular interaction in solution. So today, she is going to tell us one piece of her work. So welcome, Naomi.
Okay. Well, thank you, Kambu, and also Oscar and John and Steve for the invitation to give this colloquium. So yeah, like you were saying, my group in some sense visualizes the nanoscale dynamics of what I'm going to call today hierarchical materials, which are very far from equilibrium, either because they can't help it or because we drive them to be. And I'll divide my time today into two different stories to give a taste of both of the primary areas we work in, basically distinguished by whether we're imaging ultra-fast energy transport or slower timescale material restructuring. So in the first story, I'm excited to describe how we're now able to follow various forms of energy or quasi-particles imparted to a material on their relevant characteristic nanometer and picosecond scales with a really powerful new optical elastic scattering-based approach in order to elucidate the impact of various forms of material heterogeneities on energy transport. And in a second story that's a little bit shorter, I'll introduce you to a flavor of soft condensed matter, where we explore electron beam-driven phase behavior of an intriguing interfacial colloidal nanoparticle system and elucidate how multiple interactions at play on a range of different scales combine and can be controlled to determine the emergent collective behavior. This side of my lab focuses more generally on the dynamic formation and transformation of complex materials imaged at the nanoscale, largely by pushing the non-damaging limits of electron and cathodoluminescence microscopy. And though the timescales of formation and transformation and of transport in hierarchical systems span over 10 orders of magnitude, one common theme is that the science in my group is enabled by our continued development of a suite of spectroscopic imaging tools that access new and, I'd argue, more suitable combinations of spatial and temporal resolution, something that's been facilitated in the past few years by the Strobe NSF Science and Technology Center in Image Science. Okay, so to begin, what do I mean by hierarchical material? So the primary feature of a hierarchical material is that its basic building blocks are not atoms alone, but already in combination, for example, as particles or molecules, anywhere from a few angstroms to the micron scale. And why would we elect to construct materials with these more complex components? Well, taking electronic materials, so semiconductors or conductors as an example, you can easily imagine how the various structures of solids formed from these components could impact the band structure in ways that are more challenging to orchestrate with individual atoms alone. So these building blocks take up space and can be anisotropic or have different symmetries than atoms do on their own, which offers the exciting possibility to create materials with new and different emergent properties. You can loosely think of it as a sort of bottom-up way to construct metamaterials with smaller characteristic length scales that couple more directly to, say, electronic or vibrational degrees of freedom. So by virtue of their shapes and sizes, the primary bonding interactions between their building blocks are relatively weak. For example, van der Waals bonds. That's what's holding this molecular semiconductor crystal together, and also this solid made of colloidal nanoparticles. What's especially multi-scale is that now you have to keep track of both these weaker interactions between the building blocks and also their additional internal degrees of freedom where bonding is covalent or ionic or metallic, so similar to traditional atomic-based materials. And an important attractive consequence I want to highlight is that generally, because these materials are held together with far weaker and less stiff bonds, they have lower melting temperatures, so can be formed either from a melt or a solution at less extreme conditions. However, the flip side is that you can assemble a hierarchical material with relative ease, but that means it can also disassemble or be less stable for the very same reasons. So these instabilities are really fascinating to study because they force us to learn how interactions or processes at various scales compete or combine in difficult to anticipate ways to yield emergent behaviors like this structural transformation that we've studied. And the final feature of hierarchical materials that I want to highlight is a direct consequence of both their finite sized building blocks and also the energy scales of their bonds and commensurate melting temperatures. So together, these yield dynamical pathways for material assembly or restructuring that are far more likely to occur very far from equilibrium compared to the way we grow materials with atomic building blocks. So for example, this often means that you end up with amorphous or polycrystalline or a combination of morphologies. It can also lead to intriguing polycrystalline structures with orientational correlations, as seen in this spherulite structure here. So that makes these dynamics especially exciting to study. There are new and diverse mechanisms to be discovered all the time, and it also illustrates that we might not even have access to hierarchical materials ground state. The structures typically formed are often strongly kinetically trapped. So that's why I'm so interested in imaging, because we have to look at material heterogeneity at multiple scales, learn how it impacts their emergent properties, for example, these electronic ones, and think hard about the protocols to employ to form the structures we want. Some heterogeneities are welcome, functional, or enable something that we want, but whereas other compromise the emergent properties. Okay, so if we really want to combine the study of structure, emergent function, and formation of hierarchical materials, I'm confident that we will see new patterns and ultimately be able to design or predict or control processes and outcomes in ways that we haven't yet imagined. So that's basically what I'm calling Hierarchical Materials 101. today, and I'll return to the questions of structure and formation in the second part of my talk. Now I'll begin the first part, which focuses more on the emergent property of transport and its relationship with material heterogeneity. Okay, so a natural question to ask is, if in these heterogeneous materials we're accepting that there's going to be some sort of disorder, then what kind would be best, and how much of it will we like so that the energy is able to be transported over distances that are greater than a single building block? And while this is a good question for any of the electronic material examples here and more, I'll also use this as an opportunity to provide a bit of background on one of the materials that will feature in a decent fraction of my talk. So that's the family of metal halide perovskites. So typically in these metal halide perovskites, you have a lead ion, and it's coordinated with halide ions that can actually be selected to tune the band gap of the semiconductor. And you can have either an atom or also a small molecule in this perovskite A site. And owing to these materials' defect tolerance and excellent optical properties, these have been used a lot and received a lot of attention in the past several years because of their rapidly increasing power conversion efficiency as photovoltaics. So really, like, already rivaling here that of more conventional silicon solar cells, though you could, in principle, very excitingly make these sorts of things in your kitchen from simple liquid precursors. So in some sense, these metal halide perovskites have, I guess you could say, democratized the production of photovoltaics in the way that Scotch tape has democratized the study of quantum materials. So generally, the films that are formed in this way are polycrystalline. So a natural question is how the grain boundaries or other heterogeneities impact photogenerated charge transport. So just as an example, which of these sorts of trajectories here is the most likely or most desirable? And how would you actually make those two things match? Experimentally, this is actually very challenging because to measure, because the carriers travel on ultra-fast timescales, and in suboptimal materials at least, may travel only distances much smaller than that of the optical diffraction limit. So fear not. So the prevailing approach to try to address this sort of issue is to employ what I like to call spatio-temporal or stroboscopic energy flow microscopies. So basically spatio-temporally resolving this photoexcited transport. So you can think of this like a time-resolved pump probe microscopy, where there are a lot of different ways of probing with various different types of light matter interaction. And while there are these multiple types, all of them employ a similar sort of pumping or photoexcitation, basically focusing with a microscope objective to create a very small population of photoexcited species or quasi-particles. And they all, on the output side, observe, in many cases, the mean squared expansion of a distribution of these quasi-particles. Though, in my view, the whole power of these sorts of approaches is that it doesn't always appear diffusive, like in this cartoon, and we can see that. Okay, so how does material heterogeneity affect electronic transport in the first place? What do we sort of expect? And I'll subdivide this heterogeneity by scale. So on a sort of mesoscopic scale, you might have different domains and interfaces between them. On a much smaller scale, you might have point defects that can serve as traps. And I should just say that we typically expect charge carriers to diffuse in a semiconductor because they scatter, as opposed to traveling ballistically. So rather than always measuring a straight diffusive curve in the mean squared expansion versus time, we expect that transport behaviors, when you have heterogeneities on these mesoscopic scales, might appear piecewise. as energy encounters different regions in space. So for example, this sort of start-stop behavior with these terraces here. And for atomic scale heterogeneities, we see different regimes, but in this case on account of changes in time due to excited state lifetimes evolving the relative densities of excitations and traps. Of course, sometimes you see both at the same time. And ideally, what we want to do is specify a finite number of classes of heterogeneities and establish models for how each of them impacts the transport or some other emergent property, just like, I've sketched this handful of different behaviors on these cartoons. Okay, so I'll describe how my group developed this transient scattering or transient reflection-based approach. I'll show you some examples of addressing those types of heterogeneities, including the use of in situ structural correlation and how the generality of scattering in particular has allowed us to not only look directly at transport, but also at the effects of energy transduction. And so the probe that we use in our microscopy is called, or was originally used in interferometric scattering microscopy that was developed by Sandagdar and advanced also by Kokura. And that's what we're going to use as our probe. It's also going to allow us to look at structures because it's an ultra-sensitive interferometric approach to typically look at very small particles and how they move around. For example, each of these is a single protein sitting on a cover slip in a microscope. And the general way that it works is that light illuminates this sample through the microscope objective, and the scattered light from the particle is collected and interfered with a sort of local oscillator, a reflection, for example, off of a sample substrate interface and detected on a camera. Okay, so it's very, very sensitive. It really allows you to see the scattered light much better than, for example, in dark field microscopy. So that is the probe that we are interested to use in our experiments. And so since interferometric scattering is the probe, but we're doing a stroboscopic technique, Milan, the originator of this work in my lab, dubbed it stroboscat. And we're measuring the properties of excited state species, but we can also, just by probing, measure the ground state, and that provides an in situ structural correlation. So the key difference here is that whereas in iSCAT, we're measuring particles or structures by first pumping the sample with a localized spot, we're measuring quasi-particles instead, like charge carriers and excitons. So we're measuring basically a differential signal. It's the difference between the amount of scattering we see when the pump is on versus when the pump is off. And that's owing essentially to a variation in the optical polarizability that the quasi-particles induce. So we can watch the expansion of initially localized quasi-particle distributions, like shown in this blue spot here. And then I should just say this is really quick. It works for a really wide range of materials, some of which are plotted here, and especially over a very large dynamic range in space and time. And from this, we can compute a diffusivity from the data with sensitivities based on the fact that it's shot noise limited to very, very small, say, nanometer changes in the extent of a distribution. But especially on a log-log plot like this, it can be really easy to hide effects of heterogeneity that are patently on display, for example, in this data series here, which is an example from a heterogeneous semiconductor. And so the real lesson of this story that I'll emphasize is that when you have heterogeneous materials, diffusivity is a bulk parameter that may or may not reflect what's actually happening in the sort of intrinsic properties of the material. Okay, so here's a quick example looking at the migration of bound electron hole pairs or excitons in a molecular crystal. So this crystal is basically made of these pentacene derivatives. So you could think of this as snipping these little strips of graphene and attaching some side groups to these little molecules in order to, try and engineer the structure and how they pack with respect to one another. So this is a polycrystalline material. You can see here there's, in the ground state image, a sort of wedge-shaped domain, and it's flanked by these two other domains. And then if we pump in that red spot, kind of in the bulk of one of the domains, we can measure a movie that looks kind of like that. And because the molecules are anisotropic and the crystal structure is too, the transport is not surprisingly anisotropic. It has a fast and a slow axis. What's more exciting to me about this is that not only can we measure it, say, that one location, but if we look at, say, the apex of this domain where there are grain boundaries, then we see much more compromised exciton migration. And even more interestingly, we see this piecewise behavior here when we look at a region that's less confined by the grain boundaries, showing sort of spatiotemporal evolution really clearly. So that's just a sort of quick example to get us calibrated. But I do want to spend most of my time talking about stroboscat, talking about this particular example here, where this is relating to these halide perovskites. We're interested to know the functional pathways for how the charge carriers flow when there are crystalline domain interfaces. Okay, so the problem is really this, that charge carriers are known to travel between different crystalline domains, but conductive AFM measurements have shown that there's an infinite resistivity across the interfaces. And also another sort of paradox is that the efficiency of photovoltaics that employ polycrystalline perovskites is higher than the single crystalline perovskites. That doesn't correlate with the diffusivities that have been measured in these two different morphologies. So we really wanted to explain these apparent paradoxes, and I'm just going to tell you the answer right away and then explain why. So what we learned is that these charge carriers that are excited near the surface of the film, when they encounter one of these very highly resistive interfaces, they basically have no choice but to sort of move deeper into the material, at which point they can find a region that has a lower resistivity, and then they can move on along into another crystal grain. So let me explain exactly why that happens. So first of all, Hannah used in situ ground state images like these to identify interfaces between domains in this halide perovskite material. And this series of stroboscat images, basically, you can see that the photo-generated charges initially appear as dark or negative contrast relative to the background. We notice that these lighter regions that show up, the positive contrast correlates with locations of interfaces. So remember, this is an interferometric scattering approach, and so if this is an interferometer, we should have access to depth information. And so what we hypothesized is that the phase of scattering is basically changing due to scatterers traveling deeper into the film at the location of these interfaces. Okay, so you can start to see where our hypothesis came from. Now let's see, we corroborated this hypothesis by performing spectral interferometry around the band edge. So basically dispersing light spectrally in a spectrometer instead of taking a picture of it like we typically do, but in the same instrument. And if we say excite on one side of an interface here and we probe either on the same side or on opposite sides, you can see that the signal that we measure spectrally has the same phase, whereas the phase is different when we measure over top of an interface. Okay, so I'll show you how we can take all of these results that are a little bit unusual in that I've been focusing on depth. And this is a stroboscopic microscopy where I originally showed you that people look at lateral expansion. Now I'll connect all of this with the lateral transport so you can see how that further corroborates this hypothesis. Okay, so here is this time series looking at the lateral properties. And if we look in, say, these different directions here, this is the mean squared expansion as a function of time. And what's interesting is, oh, it's certainly not diffusive, but it is sort of piecewise, right? Like I showed here with this sort of stop and start motif. So what we think is happening is that initially you just have free diffusion within one crystalline domain, but then encountering an interface pauses on the lateral transport, and that's when we see these brighter contrast spots show up. But then at a certain point, these carriers find a way across the interface deeper into the film, and then they can continue to diffuse again. And that happens until essentially they all get trapped. And in this case, the lifetime of these carriers is about an order of magnitude larger than this. It didn't seem very exciting to keep on going, but this is also a way to be able to measure the fact that there are deep traps in these materials. Okay, so that's basically the way that we arrived at this idea of these charge carriers having to go deeper beneath the film and that there might be a resistivity profile at these interfaces that looks something like this. And this is actually something that could be really valuable in terms of thinking about, how you make solar cells out of these materials. Okay, so one potential way to extend the migration length of these charge carriers further is to try and extend the carrier lifetime, for example, by manipulating the band structure. And that's something that Hema Karnadas's group did here by alternating the metal at the center of these octahedra. So that, in this case, with these metals, generates an indirect band gap as calculated, as it turns out, by Marina Phillip when she was a postdoc in the Neaton group. Okay, so stroboscat shows multiple temporal regimes. So we hypothesized that bromine vacancies, in this case, were creating shallow charge carrier traps, and that initially the carrier density exceeds the trap density, so that we can essentially demonstrate the intrinsic diffusivity. And that once the traps are no longer saturated, we're observing lower diffusivity because we observe hopping among these traps. Okay, so suspecting that these traps are bromine vacancies that are concentrated at the surface, Milan cleaved one of these beautiful crystals and measured at a fresh surface, and he showed that this enhanced the diffusivity in both of these two regimes. So this is very cool in the sense that already with these traps present, the migration length was greater than a micron. And then if there were a way to get rid of those traps, then on a more permanent basis, then you could gain another order of magnitude. Okay, so that's all I'll say explicitly about heterogeneity today. But what else does transient scattering get us? So I told you initially when I introduced this stroboscat approach to you that the way that we were sensitive to these dynamics of these quasi-particles was by virtue of how they modify the electric or the optical frequency electric polarizability. So let me just unpack that in a little more detail to show you some other things that we are capable of doing with it. So first of all, the field from the quasi-particle distribution should induce some spatially dependent medium polarization. So you can think of these as all your little bound oscillators oscillating at optical frequencies, as we typically do. And then we need to think about what happens when the probe shows up. So you have this spatially dependent quasi-particle induced medium polarization. And this perturbs the interaction with this external optical field. So what I'm really asking is, how much easier is it for the optical field to do the polarizing of these little dipoles here, rather than whatever the quasi-particles are doing to constrain them? Is it easier or is it more difficult? Okay, so in our experiments, because we're probing in the optical, we're interested in looking at changes to the optical response that we might measure in the ground state on account of the presence of these quasi-particles. And so the reason that we might see a dark contrast in our microscope would be if the medium becomes more polarizable in the case where there are quasi-particles present, and we're sitting on the blue side of the resonance. If we moved instead and probed on the red side of the resonance, then we would see a pi phase shift. And what's cool is that if the medium becomes less polarizable, then we should see the reverse. So essentially, we have the power to choose what sign of contrast we measure. I showed you basically dark contrast so far, but we can choose that based on the sign of the detuning. Now, where might that be useful? Well, it's definitely useful if you're interested to know about heat in your sample as well. And here I'm thinking about heat in the context of, say, a lattice expansion or contraction. So this is really a DC contribution. So that can, in principle, have two different signs as well. But we can always select the sign of the electronic quasi-particles to be opposite of what we measure for heat to look like. And that's something that we've done in both directions here, for example, with silicon, and then also in this few layer molybdenum disulfide that I'll talk about shortly. Okay, so before I do that, I want to give you one example, just looking at thermal transport on its own in films of a few nanometer gold nanoparticles. Okay, so when photoexcited hot electrons give energy back to the gold lattice, you can think of this as like basically instantaneously happening on the timescales of heat transport that we're interested to measure in this film. So stroboscat uniquely enabled James to see subdiffusive heat transport. In other words, the mean squared expansion is scaling sublinearly with time, as opposed to what you would see in, say, pure gold. And so what causes this non-diffusive behavior? So James recapitulated the behavior in simulated heat transport, including three different components. So these slightly disordered gold particles, they're ligand shells that are basically the coating on them that helps to suspend them when they're sitting in a solution, and these voids based on this TEM image. So in order to rationalize the behavior, we learned that the heat transport is essentially diffusive within the boundary conditions or the confinement that's introduced by these voids. And to do so, James realized that he could reframe the transport in terms of the geodesic distance from the origin where the heat was generated. So basically the shortest distance to a point through the actual material. And diffusive behavior is actually nicely recovered if we plot the mean squared geodesic distance as a function of time. So this is a cool result, in my view, not only because it wasn't previously possible to spatiotemporally resolve this impact of disorder, but also because we suspect that this subdiffusive process, even though it's scarcely been measured, is really quite common. Unfortunately, that means that more conventional heat transport measurements, which people use in bulk, will give a different answer depending on the length or time scale on which they're done, which could be especially concerning for, say, nano or microstructured devices if they contain imperfections. But at least now we know. All right, so onto the simultaneous presence of electronic species and heat. So generally, those of us who use pulse lasers are keenly aware of the fact that we might be unintentionally imparting heat to an electronically excited semiconductor through higher order processes like annihilation or Auger recombination. It can be challenging to tease apart electronic and thermal contributions to an optical signal, and it's especially important in low dimensional systems like few or monolayered transition metal dichalcogenides, because heat that would otherwise disperse in 3 dimensions is confined to fewer dimensions. So this really begs the question of how does heat impact the electronic evolution, or possibly also masquerade as it. So in few-layer transition metal dichalcogenide molybdenum disulfide, Hannah imaged a rapidly expanding positive contrast signal that's consistent with the diffusion of electronic species, and the negative signal you see is basically stagnant on these similar timescales, which we expect is dominated by heat. This is especially valuable because others, for example, Alexei Chernikov's group, have hypothesized from spatiotemporal photoluminescence, where they can only see the electronic contribution, that thermal gradients can drive excitonic diffusion, and show that these effects kick in at extremely modest densities. So now we can see the heat, plus we can see it in tandem with the electronic signatures. And it also appears that we can spectrally isolate the heat in order to fully dissect the interplay of these two different forms of energy, and also potentially to learn more about the Auger dynamics themselves. Okay, so in this first slightly longer part of the talk, I hope that I've persuaded you of the power of stroboscat and all of the ways that it helps us to make connections between the heterogeneous structures of materials and their emergent, especially electronic properties. And we talked about heterogeneity in a number of different contexts. So for example, like full confinement, or temporary confinement, or much smaller scale atomic defects, or even just the molecular scale packing in molecular crystals. And in all of these cases, we were able to learn about different phenomena that are very different than what one might expect in bulk, and to leverage different aspects of our technique. So we learned that it really matters what scale you're measuring on when you look at subdiffusive heat transport. We took advantage of depth dependence and learned about resistivity. We took advantage of just playing around with the population densities of quasi-particles to extract intrinsic parameters, and we also were able to see anisotropies in materials. So that, combined with the fact that by really thinking a little bit more carefully about the optical contrast and how it's generated in our microscopy, gives us information not only about electronic signatures, but also about heat, is super cool to me. And I guess the ultimate lesson of this part of the talk is really that if you're looking at a heterogeneous material, you've got to be really careful to use bulk parameters like diffusivity. So there are a number of different directions that we're interested to take this sort of work in the future. I guess I already talked about leveraging the contrast mechanism. My lab is always interested in anisotropies, and there are a variety of different systems that we're launching into to think about measuring different types of transport anisotropies. As Kambu mentioned, we're interested in some living things too. So in particular, we'd love to be able to do these same sort of measurements to try and learn how the efficiency of energy transport in the very first picoseconds of photosynthesis is pretty much unparalleled by anything that can be made by a person. And then on much slower timescales, we've actually just started to think about ion transport, as well as might be relevant to solar fuels or solid state battery electrolyte, or maybe even electrophysiology. Okay, so that's all I wanted to share with you today about resolving transport amidst the various heterogeneities of these hierarchical materials. But next, I'd like to return to the much slower dynamics of the formation and transformation of these materials. And before delving into one example in detail, I'll show you a single slide to give you a sense of the richness, again, of employing nanoscale imaging, here to elucidate the mechanisms for various types of phase transitions, in particular, again, centering on examples from the metal halide perovskite family. Okay, so we've been working over the years to extend the applicability of cathodoluminescence microscopy, so basically mapping the light emission in a scanning electron microscope. So extending this applicability to soft materials to not only image their optical properties at the nanoscale, but to follow their dynamics non-invasively, essentially by doing things like increasing light collection efficiency and substantially lowering the electron dose. So these two examples I'll show are emblematic of what we can do. So determining mechanisms of two different phase transitions in these halide perovskite semiconductors, especially in collaboration with my colleagues David Limmer and Pei-Dong Yan. Okay, so here's one example where Connor imaged a thermally induced structural transition to the perovskite phase from another structure in these rods that's so different that the halide ions have to actually diffuse through a liquid-like interface for it to happen. So this is definitely like a multi-step process, but it's one that we can quantitate. And a really cool feature that we discovered thanks to simulations by Fan from Michael Grunwald's group is that despite the apparent disorder that you see here at this interface, ion correlations are strong enough that the emergent perovskite always orients in the same direction with respect to the original phase. Okay, and second, together with David, we uncovered a Polaronic mechanism for a photoinduced phase transition in halide perovskites containing a mixture of two different halides, for example, here in blue and gold. And these luminescent spots that you see here each correspond to a single photogenerated charge carrier that's locally straining the lattice sufficiently to make a little solid state quantum dot by locally stabilizing a demixed phase that's enriched in the halide that generates a smaller band gap. So before we imaged this process, it had been envisioned as a sort of traditional phase separation with two macroscopic phases. And I think it's really cool that when the material is illuminated, the spots that don't light up look just like they would in the dark, but that you can hop around just like right next door, and the charge alters the material composition and structure to make this little like nano beacon, thanks to pretty substantial electron-phonon coupling. Okay, so that's just to give you a little bit of a taste of some of the things that we can look at in these sorts of materials. But returning to my initial description of hierarchical materials, I'd like now to consider the question I posed. Can we really characterize and understand these materials well enough to predict and control them? Okay, so moreover, can we drive a system away from equilibrium in a controlled way to positively impact the structure and stability? So this need should now be especially clear given the examples of the instabilities I showed you on the last slide. And to try and answer this question, I'd like to turn to using a model system composed of spherical particles, and we'll deliberately drive phase dynamics and ultimately disassembly in order to elucidate the nature of the multiple contributing interactions that can now, as a result, help us devise strategies to assemble similar systems. Okay, so here's the setup. We make a model 2D material out of silicon nanoparticles. It's initially, as you can see here, a defected solid that's pinned to an interface between an ionic liquid droplet and the vacuum in a scanning electron microscope, and it's essentially motionless. So we use the electron beam, therefore, to excite the system or to impart energy to these particles, but also to watch the ensuing phase dynamics. And just for reference, an ionic liquid is essentially a room temperature molten salt that's made of finite-sized molecules. You don't have to remember what they look like. And these molecules together in this solution have very unusual properties in their own right. So here, for all intents and purposes, you can think of it as a dynamic screener of charge, a sample grounder in our SEM, and it also has a very low vapor pressure, so it sticks around. We repeatedly raster the electron beam, so it visits, one particle or one pixel once per movie frame, and here's what we observe as we make this sort of movie. And of course, our goal in making these movies is to then try and explain what's happening. Okay, so here's a montage of these dynamics, and you can see that we certainly started at a higher density and then moved to a lower one. So we want to be a little bit more quantitative than that. And I'll just tell you up front, there are 3 interactions that we're going to need to focus on. So interparticle interactions, the interaction between the electron beam that's driving the dynamics and the particles, and then also the interaction of a particle with the interface. And that makes it sound really simple. It actually took a lot of effort to isolate them this clearly and also to determine how they balance with respect to one another. Okay, so color coding this same data set by the magnitude of the bond order parameter, so general metric for local hexagonal symmetry, illustrates to us that there are 2 different stages. So coarsening, so the amount of yellow or high value of the bond order parameter is increasing, and then melting, where the yellow completely disappears. There's no time to show you the phase of the order parameter today, but it's also very cool. We've also put a lot of effort into looking at coarsening in that way, but today I'm instead going to focus on melting. Okay, so based on this character, it's natural to ask what variables control melting in this driven system. And the answer up front, what we learned after a lot of head scratching and investigation, is that the changing area fraction drives this process. So this raises other questions, of course. What controls the area fraction? What model captures both the nature of the interparticle interaction and the resulting phase behavior? And how does the electron beam actually do its job? How does it influence these dynamics? So we tried a lot of models to self-consistently describe our observations and the role, of course, of the electron beam. And I'll focus on the one that's most consistent, folding in each of the necessary considerations in sequence. So to start, assume for now that the area fraction can be controlled, and I promise I'll return to this and verify that assumption too. Okay, so here are binarized maps at 3 different times of the same data set. So here blue is ordered and yellow is disordered. And John's simulations recapitulate this behavior really well. So while your initial guess might have been that the dynamics are dominated by something like interparticle Coulomb repulsion, the simulations required not only repulsion, but also a weaker long-range attraction, which is captured in a 612 or Leonard-Jones interparticle potential. And so we really do need this attractive force as well. We can't just use, say, a hard sphere model like one might use for many other colloidal systems. So we added to that a phenomenological particle deletion protocol that basically follows the experimentally observed reduction in the area fraction as a function of time. And interestingly, we don't have to change the Leonard-Jones parameters as a function of time, even though the electron beam continues to illuminate and drive the system. Okay, so the system seems kind of immune to those. And so interestingly, the decreasing area fraction basically drives the melting, so basically translating horizontally somewhere on this phase diagram, but not changing anything vertically. Okay, so it helps, however, to be a little bit more quantitative than that. So I'll show you 2 of the parameters that we use to do that. First, here's good agreement in the evolution of the ordered in blue and disordered in yellow fractions of the system. Okay, so that's good. But to be even more precise in terms of characterizing the melting, we can employ a so-called Lindemann criterion. So traditionally, the so-called Lindemann parameter diverges when melting occurs. And John adapted the Lindemann parameter so that we could keep track of individual particles as a function of space and time. So in particular, sort of frame to frame, all at once. And this is basically a parameter that's capturing the degree of motional correlation of the particles with their nearest neighbors. So you can definitely see here that the persistent fluid phase develops, especially in these latter three frames. That's the maroon color above a given threshold. Okay, so this instantaneous Lindemann parameter was really essential to refine the match of simulation and experiment. So first, looking in aggregate, like over the entire region of interest, shows correspondence of the divergence. This is a much more stringent test than just looking qualitatively at the images. It also pinpoints the specific trajectory that the system takes on the phase diagram. So it turns out to be consistent with a supercritical transition from solid to fluid. Okay, so what have we learned so far? So we focused so far on the interparticle interaction, which we've now captured in a fairly simple model involving this Lennard-Jones potential. And we found that the decreasing area fraction drove the melting transition. So by inference, the electron beam must be implicated in reducing the area fraction. So I'll next explain how, by focusing on these other two interactions in this problem, we can try and build the rest of our model. Okay, so here are two important observations to help us get started. So first, we're pretty sure that particles disappear by sinking away from the interface, which you can see highlighted in this yellow circle here, not laterally spreading out over the field of view. And the second thing is very cool. By driving and observing the monolayer dynamics at different electron beam accelerating voltages, so 5 down to 2 keV, Connor found that particles sink faster, or the area fraction decreases more quickly when a lower energy electron beam irradiates the particles. And so the question really is, how come? And to explain these differences, John Rabin and Connor simulated the behavior of the dose of the accelerated electrons as the beam scans over the particle, showing that the net total charge on the particle and the average particle sinking time are correlated to one another. So at higher accelerating voltages, for example, at 5 keV, the beam fully penetrates the particle. The trapped electron charge and the positive holes that are left behind closer to the surface from scattering events in these insulating particles leads to a minimal net charge. But at lower accelerating voltages, the stopping distance in the particles really decreases a lot, and energy and charge are way more concentrated at the particle surface. And actually, there's something like a 20-fold more accumulated charge at these lower accelerating voltages because the electrons don't make their way through the entire diameter of the particle like they do at the higher accelerating voltages. So essentially, with these experiments, by varying the accelerating voltage, we were able to vary the accumulated charging rate, and making that connection enabled us to specify the effect of progressive electron beam exposure as a function of time at a given accelerating voltage, this being the series that I've been focusing on primarily here at 5 keV. Okay, so from all of this, can we, well, I guess the question is, like, we can deduce that the more that a particle is charged, more likely it is to unpin from this ionic liquid vacuum interface. And so now let's talk a little bit more about how. Okay, so this is going to become more complete once I talk about interfacial interactions as well. But for now, just focusing on the charging alone, I'm sure you'll appreciate that, you know, if you have a charged particle and it's partly exposed to vacuum, its field field lines that go through the vacuum, can't be shielded. And this scenario is likely not the equilibrium state of the system if there's substantial charge on the particle. So given we already saw that the interparticle interactions don't change as charge accumulates on the particles, so as time evolves, the ionic liquid must be doing a really good job at being an ion conductor, which it is. So not only will these ions here in the liquid reconfigure in order to shield the charge that's on the particle where at the surface, enriching the anion content near the particle surface, but being able to screen a higher surface area of the particle definitely seems like it would be more favorable, like maybe something that looks like this. Okay, so considering the electron beam driving interaction, what we primarily learned is that the area fraction depends on the amount of deposited charge. And the last ingredient we have to include in a model to describe the progressive disappearance of the particles from the interface is, of course, the surface interactions themselves. If there weren't any surface interactions, we clearly wouldn't be able to stabilize particles at the interface in the first place. Okay, so in general, the equilibrium configuration of an uncharged particle relative to a fluid-fluid interface like this one can be determined by comparing the surface interactions of the particle with each of the fluids to the fluid-fluid interaction that would occur in the absence of the particle itself. And so here John parameterized it in terms of the contact angle the liquid makes between the particle surface and the interface it makes with the vacuum or the vapor. Right? So when there's a charge on the particle and the ionic liquid reorganizes near its surface in order to screen the charged particle's field, we already inferred that the contact angle should change. This is really equivalent to saying that the particle goes deeper into the liquid because more of its field can be screened. Right, so that's basically, like what we're saying right here. The dependency of the change in contact angle as charge is added to the particle can be encapsulated in this Young-Lippmann equation and is the principle behind what we would typically call electro wetting. Okay, so electro wetting normally refers to what happens to a liquid at a surface when a potential is applied to that surface. But John realized here that the electron beam is generating the potential and that he could combine the dependency of the pinning energy on contact angle and of the contact angle on surface potential in order to determine the pinning energy as a function of the surface potential. So you can think of this increasing scale here in the surface potential as a proxy for the progressive charging in time. So initially, there's essentially or close to no charge on the particle, and we estimate that the pinning energy is very, very strong. So, several tens of eV, or over 1,000 times the thermal energy, kT, at room temperature at least. And as the electron beam repeatedly scans over a given particle, the surface potential increases, drawing more ionic liquid to cover the exposed particle surface and decreasing the contact angle. And then at a certain point, the pinning energy is decreased so much so that it's comparable to this thermal energy, and it's readily unpinned, decreasing the area fraction. Okay, so by considering the interaction of a charged particle with the interface, what we have now deduced is that the increasing charging-induced surface potential decreases the contact angle of the particle until the particle just completely unpins. And I personally think it's just super cool to see how these three different interactions combine and balance, which was absolutely not obvious to us a priori. So to connect all the dots and finish things up from all these different parts of the model, Initially, the particles are initially close to charge neutral and are strongly pinned at the interface. They interact with one another through a Lennard-Jones potential. And then the electron beam charges the particles and the monolayer coarsens. And as the electron beam continues to charge the particles, they're screened more and more by the ionic liquid until they're unpinned. And this is basically causing a decrease in area fraction that's leading to this melting phase dynamics that we observe more macroscopically. Okay, so I think there are a lot of cool things that we can learn in addition to what I just shared with you. You can definitely see that this is a rich area and that we can make it even richer, for example, by playing around with the shapes and sizes of particles, or even, as Rebecca recently showed us, by playing around with these binary mixtures of different sizes. We're also really interested in more manipulating that we might be able to do now that we understand what the electron beam is doing a little bit better with these particles. For example, here we're basically disrupting a gel and ordering it and densifying it. I didn't get to tell you much about the coarsening side of things from the data set that we were looking at, but we are curious to know if the coarsening is anomalous or not. We're also interested in annealing by other means. So for example, by dipping into the really active current area of active matter, so basically self-repelling particles, and using them as dopants to see if we can simulate various annealing procedures for passive particles themselves. And then finally, we're also interested not so much in scaling up, but scaling down. So we have ongoing work in my lab looking at Coulomb-mediated assembly of strongly coupled nanoparticle superlattices, where these nanoparticles are 2 orders of magnitude smaller than the ones I was just talking about. And these are really cool systems by virtue of having very strong coupling, which can be challenging to orchestrate in these materials. You can make macroscopic superstructures like these, and we've been busily trying to explain the complex mechanisms associated with the formation of these sorts of structures, why we can make them when we have, say, metallic particles, but not so much yet with dielectric ones, something hopefully we can change by manipulating, perturbing, and controlling. Okay, so hopefully you don't think I'm too controlling. I just want to thank you again for the opportunity to share a few forays into what I'd like to think of as the intrigue of hierarchical materials. And I hope I persuaded you that we've developed some tools and models that allow us to dissect many of their properties, and that there's definitely more to be done. So thanks very much for your attention. And of course, nothing would be done without this wonderful collection of people here, many of whom are actually here, which is always kind of exciting and also terrifying. So I just want to thank my group and all my collaborators for their talent and dedication, and especially for their resilience during these times. And I hope I've mentioned all of the primary contributors to the work as I went along, but I've tried to highlight things in terms of the different stories that I told. And seeing the time, I should probably stop here and see if you've got any questions. So thanks very much.
Well, thank you, Naomi, for the very interesting talk. So now it's time for questions. So please raise your hand and wait for your turn to ask question. Okay, let's see. Samuel has a question.
Hello.
Hi, Sam.
Yeah, so maybe this is a strange question, but about these self-assembled spheres, silica nanospheres, where you're showing melting, and you pointed out that essentially like in many phase transitions, the impetus for the phase transition is the formation of a defect, right? But in this case, you form the defect by changing the density, by having these particles sink. So my sort of annoying question is, in 3 dimensions, the particles can't just disappear. So how much of this is analogous in, let's say, like a three-dimensional colloidal system, where on one hand the particles have nowhere to go, but on the other hand the density phase transition might be less dramatic because you're in 3 dimensions, and so the entropy of melting is a little bit lower.
Mm-hmm. Yeah, that's a really interesting question. I mean, obviously, two-dimensional systems are interesting to many people in their own right, but I think that you still have surfaces. And so, whereas in some cases in 3D, you would expect a defect that's internal to the three-dimensional structure to start things off. Certainly you have surfaces here, and you could imagine a situation where you're losing particles from the surface, or the surface itself is basically enucleating the process. So I guess that's the connection that I would want to make in this case.
Any other question?
It looks like there might be a question in the chat.
Chat, okay. Let's see. Oh, yes. Alex has a question. Back up a bit. Would you include in your, let's see, material framework biological lipid layers? That's it's a very long question.
Okay, yeah. So I just opened the chat, and I can take a stab at this. So yeah, the question is, in the sort of classification of hierarchically scaled materials, can we include things like lipid bilayers or cellular membranes, and especially with their very selective transport characteristics? So like crossing membranes through pores and things like that for signaling. Yeah, so I would absolutely say that a lipid bilayer itself is a nice example of hierarchical material. So like the lipids themselves are your building blocks, right? And they will interact with one another. And in some sense, it's very connected to what I was just describing, because it's also an interfacial problem as well. So yeah, absolutely. How you then think about crossing the bilayer through pores and whatnot, and that's a very short distance. I'd need to think a little bit more about that. But certainly you could imagine that if in your bilayer you don't just have lipids, but you also have a whole bunch of proteins or various other biomolecules that are associated with some part of the bilayer, that you will have to navigate around them. So like one experiment that I always thought would be super cool to do, maybe Alec knows about things like fluorescence recovery after photobleaching experiments, where you would basically have, fluorescent lipids and, sort of bleach them in a particular spot and then measure diffusion as the fluorescence recovers in this spot, because before fluorescent lipids diffuse back into it. It'd be very cool to be able to do measurements of that sort on these sorts of hierarchical systems, but on size scales where you didn't have to bleach a diffraction limited spot. So that's something that's definitely been on our minds, though I don't have a specific idea for exactly how we'd want to do that. So Alec also asked, can stroboscat help here? I think that we could certainly try and use it to do this sort of thing, or namely we could use iSCAT on its own in order to do this sort of thing, just given the timescales being so short. But that would still be diffraction limited. So I think what might be cool in this case is if you could do that sort of measurement without having to fluorescently label and just use some scattering property instead. That might be a cool way to do it. But yeah.
So any other question?
Well, maybe I will.
Well, maybe let me ask you a very naive question.
Sure.
So normally, how fast do you probe the system?
Mm-hmm. So like, what's the time resolution?
Yeah.
So, I mean, in some sense, it can be arbitrary. So you probe it as fast as you need to. And I guess what I would say is that, so with the current implementation that we typically use, the technology that we're using has time resolutions on the order of, or like pulse durations on the order of 100 picoseconds. But we've also experimented a little bit with using a shorter pulse laser source that's like on the same optical table for doing probing. We could also do that with pumping, and then we could get down to something, at least 3 orders of magnitude shorter than that. The tricky part is just that like you need to worry about coherence length in order to do the interferometric part. But I think that still like 100 femtoseconds, it would probably work out decently well. Yeah, we can also go out to very long time scales. That's sort of arbitrary as well.
Yeah. Okay. Okay. All right. Well, if there is no other question, okay, let's thank Naomi again for a wonderful talk.